Maybe I'll start to answer your remark, Howard, about write back and of a single node. Cluster is absolutely important. However, we have very large customers that use us in a write back mode, and they use us because of write back mode, because, for example, they use it for consolidation data from remote offices, remote stores. And in this case,
and if it blows up, they can just ask for it again.
Exactly. We have Exchange user, enterprise, and they use application level replications. So we have very large banks, users, corporations that use it in write back mode. And the message is this: if it is a read mostly workload, let's add memory. But write back is very important. We'll talk about cluster later, definitely. Okay, just view inside our driver. It is, as Rich mentioned, it is platform-independent caching engine that works without any modification across all platforms with narrow API to shim layers that provides for us glue to target operating systems. Being more specific, for Windows, it's a load driver for class of volumes. For Linux, it is a block device. We create shadow device. For VMware, it is, as Rich mentioned, loadable kernel driver. And I would say it's the only implementation in the world, except of VMware, then somebody runs really inside kernel, except of rare exceptions like Cisco, something like that. But third party, yes, we're the only company that do this. You will see that it's extraordinarily important for our product, ESX product. This interface is very narrow. As you can see, for Windows and Linux at a block level, and for VMware, it is a VMDK level. Actually, it's not just VMDK, it is extent level. You're familiar with VMware terminology, right? So it's a VMDK, which is a virtual disk. Extent level. And actually, we can accelerate separately. We can accelerate base only. We can accelerate top only. We can accelerate everything. If we accelerate base, all link clones can be automatically accelerated, and so on. This is one of the advantages being inside kernel. By the way, it allows us to support VDI, because if you are in VMDK level, do you want it or not, you duplicate cache because you don't have visibility on extent level. So each piece of design that we have is really, it's very well thought out. Next, please. Oh, by the way, I forgot to tell you about previous slides that obviously we support NAS and SAN, storage for VMware. It is important. For example, if you are on PSA level, you cannot support NFS just because you cannot see it. But because we are the loadable filter, and from Viscasi immediately request comes to our level, we support any data stores without any exceptions. Now a couple words about cache architecture that we have. So from the very beginning, we decided not to develop buffer cache design when cache is divided on a fixed size pages, I would say. Why we decided not to do this? Because we understand very well that we must avoid data fragmentation on SSD as much as possible. Because of that, we write always variable block sizes, and cache is a circle buffer. We have here read-write cache. One of the fundamental principles in our design, we never ever, and nowhere in our design, we have static allocation. For example, ratio between read and write cache. It's dynamic. Yes, we can give some advantages to write cache, we can give some advantages to read cache, but there is no hard divided. This is for read cache, this is for write cache. Who knows how workload will change? So this is a read and write cache, and this portion of the SSD for newly arrived writes. When amount of dirty data here getting reach some threshold, we start flushing, and of course when we flush we have all just thinkable optimizations in this case. Coalescing, write cancellation, reordering, much more. And based on this design as a circular buffer, writing variable block size, we minimize fragmentation for sure. We minimize amount of data. When we write on SSD, we write just one piece of metadata that describes, let's say, the whole megabyte that we're writing, and that's it. Furthermore, when we write on SSD, we sequentialize random writes. If I have write for this VMDK, this VMDK, this VMDK, I use VMDK of volume, which is for us, because it's caching, platform-independent caching engine. Actually, for us, it's just an object that we accelerate. Volume for bare metal, or virtual disk for virtualized environment. So we write coalesce data on SSD. We coalesce them. I'll explain you how we coalesce this a little bit later. And we attach the small metadata header and maybe footer, depends on SSD design. Sometimes we need a footer to satisfy SCSI requirement. We minimize amount of metadata, reduce fragmentation, and on our level, because it's a circular buffer, there is no garbage collection. Next, please. By the way, any questions, anytime, welcome. Now, even though we minimize amount of metadata, we still, because cache is huge, 1 or 2 terabytes, we yes, please.
I was still building my question.
Yes, sure.
The question about new garbage collection. You are treating the reported size of the disk as though it were the true size, and you're filling it up to the point where you hit that free space limit that you've determined, and then at that point you consider the buffer to be done, flush to disk, and restart the process?
Restart, I would not use this term, because we constantly write, flush, and clean.
How do you get around the disk's possible built-in garbage collection after you've written the volume of the disk a couple of times? How do you get around write amplification?
I would like to talk about offline in details, what we can do for that.
Okay.
But let's say we take SSD off the shelf. They already have garbage collection internally.
Right.
However, if you write sequentially on SSD, they pretty much do not have garbage collection. Nothing to collect.
Until you get to the point that the disk is full, right?
After that, anyway, we write sequentially. If you write sequentially, there is no garbage collection.
Well, the FTL should be responsible for distributing the writes across everything, right? I mean,
The
SSD does it itself.
If you send it data sequentially, the FTL is going to fill up a page.
Exactly.
Then it's going to fill up the next page.
It's below us.
As long as you continue to write sequentially, when it comes time, it's going to erase that first page as a whole page. What we imply garbage collection to mean is that there's I have no blank pages. I need to create a blank page. I have these 3 pages that have partial data. I'm going to combine that data onto one page and erase the other 2. If you always write sequentially, you never need to do that because you're always writing and erasing
to the size of the erasure
full
block.
pages at a time. Yeah.
Okay. All
Thank
right.
you.
Thank you. Sorry.
Exactly. And it will be very useful for second part of our discussion, by the way. However, sorry, I'll use...
Did you guys bring Howard? Did he come with you, or is this...
Okay, second part of our discussion. And if you allow me, I'll use however frequently today. However, if you have already dirty data in a cache, because SSD, no matter what, anyway, sequentialized random IOs, and we have data, dirty data here, we overwrite it in place. And in this way, this is a way for us to minimize unnecessary eviction of data from SSD. But I reserve time in our offline meeting, and we'll return to this. It's a very important point that you brought. However, even though we minimize amount of metadata, cache is so big, we have a lot of metadata. And of course, we have metadata in a memory to speed up, but we have cache of metadata in a memory. We keep in the memory only hot metadata, and we swap out on SSD. Just we insert it into the same circular buffer metadata when cache is getting full and we need extra space for metadata pages. However, CPU utilization is very low. We have balanced tree internally. Tree is very flat, and it is efficient design. Cache is dynamically grown, shrinking, depends on necessity, how many metadata misses we have. If we have extra misses, we add cache. If everything is fine, we decrease it. So altogether, after all, our metadata cache, our intermediate buffer for read cache, our intermediate buffer for flash, because when we flash, we read from SSD and write on the disk. This is a default maximum, can be less. And this is sufficient enough for enterprise applications and for VMware environment. Next, please.
Did you want to talk about persistence?
Yes, thank you. In write-through mode, but obviously for write-back mode, we have cache persistency. In write-back mode, we cannot say, oh, you know what, our cache is not persistent because machine will crash and we'll lose your data. Even for read cache, our customers like the fact that when machine reboots, cache is still warm. As I mentioned, how we deliver this persistency. When we write data, we attach metadata, right? So even if machine crash, and we write it as one piece, even if machine crash, we have metadata. However, if machine crashes and back, we do not want to read the whole entire cache and to rebuild our metadata. We write what we call snapshots, snapshots of metadata. Periodically, we write on SSD snapshots. And these snapshots, it's condensed content of our metadata. If machine crash, we jump into the latest snapshot, read latest snapshot, play only writes that are not a part of this snapshot, and we recover in milliseconds metadata. So recovery doesn't take 10-15 minutes as it takes for companies that I don't want to mention. It's really milliseconds. One more important thing probably, overall, we discussed it in the very beginning of FlashSoft, and we decided absolutely not to use memory as a cache. Because, as Rich mentioned, application knows how to use memory better than cache. So let's leave as much as possible memory for application. Let's leave it for buffer cache, for database. Let's use it for cache for exchange. They will use this more efficient than us. So we use memory only as a cache of metadata and never use it as a cache for data. Okay, next please. there is something interesting here. Probably we support all SSDs, all form factors, obviously. For us, SSD is just whatever is assigned to be SSD. What's interesting in read-write gates, typically SSDs, and almost all SSDs, they do not want to mix reads and writes. It's better reads only, writes, reads, writes. So we do. We open read gates and handle some reads. Close read gates, open write gates, and handle some writes. Number one, it improves aggregate performance, but it has also interesting good side effect. When read gate is opened, we collect, we queue write requests. And when write gate is opened, we have multiple writes already queued. We just create scatter gather list across all data that we have to cache, across all volumes, across all VMDKs. And from user buffer, we do not copy it to our buffer. We do not have intermediate cache for writes, no way. But we create scatter gather list for buffers in a user space and write in one piece with one small piece of metadata.
And if you're write back, you only acknowledge once it's written.
Yes, when it acknowledges it, bam, 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 done for all of them. We improve about 15 times size of block that we write on SSD having this trick. We write really large blocks on SSD. SSDs love large blocks for obvious reasons. So read-write gates works here, and we have tons of tunables that allows us to tune for different type of SSDs and different type of workload. And unfortunately, we don't have time to talk about these tunable parameters, but it's a separate topic, and we can talk about this.
So do I tell FlashSoft the page size, so it writes in multiples there?
Say again, please.
So do I tell FlashSoft the SSD page size, so it writes in multiples there?
Not in this moment, but it is very important. We have one tunable parameter, 4K aligned or 4K not aligned. If for some SSDs you start to write random writes without 4K page boundary, performance is 20 times worse. Just same about data in the memory. It must be 4K aligned. They tune it for that. And we have all tunable parameters that allows you to, by the way, default is 4K alignment in the memory, 4K alignment on SSD, but you can turn it off.
So what happens to latency if you're in a very light write time and you're kind of waiting around for more data to accumulate?
Never ever.
Okay.
If we have one write, we start one write.
Okay.
Never ever. It's absolutely unacceptable. In enterprise, absolutely unacceptable. Because we have very, very large customer. They need latency and throughput, but latency first of all. And it's interesting that we have some parameters that works very well for throughput, aggregate throughput, and some parameters for latency. And for example, we have another customer that put redo undo lock, Oracle redo and undo lock under acceleration. And for them, there is absolutely unacceptable to wait when we collect several writes. I have one write, write it. Anyway, sequentially, but write it. Okay, next one. By the way, I like your questions. Please, just.
So search the tunable parameters. I don't want to go into all of them, of course, but tunable, is that tunable by the customer, or do you do it while you set up the software?
Okay.
Or is it automatically tuned?
We have some parameters that are automatically tuned. We'll talk about this in the second part. Typically, what we do in the customer side, we start with default parameters, collects tons of statistics, and after we look at these statistics, and we can say, okay, we recommend you to increase metadata cache size like this. Let's say we we recommend you to handle in bypass mode writes that are longer than 128K, and so on. And after, with our expertise, of course, we analyze typically database, SQL or Oracle workload, specific workload, and we give recommendation. After that, without rebooting or stopping application, you can on the fly change parameters.